All right. Okay, so welcome to ME 4611. This is the second week of presentations, and today is February 5th, 2015. My name is Alec Rozas. I'm the Toastmaster for today. And for the first, to open this presentation, I'd like y'all to think back to last week. We had 3 table topics last week, and each of them had some sort of theme running through the back, having to deal with privacy or breaches of data or similar. So I'd like to invite Alec Rozas to come forward, and my question for her is that with the 3 table topics last week, as I mentioned, there's been breaches with data, but we've been using these technologies as a way of simplifying tasks. So Alec, is there a point at which technology sort of makes tasks, I guess, less secure for humans?
I definitely think that there's a point when technology starts to overcomplicate our life rather than what its main benefit should be, which is to simplify our lives. So when you have enough things like emails and enough passwords and enough accounts, then obviously this gives someone the ability through the internet, from pretty much any point on the world, to access your private information. This is supposed to be a convenience for us, which it is, but because of that convenience, it does open up the possibility for someone else to access it. I think that in today's world, technology is also a necessity. It's something that you can't really live without anymore because you don't really have the option. This is the way we sustain our day-to-day life. And so then therefore, even further, you don't even have the choice to avoid it. So for other people that are interested in gaining access into those private areas, they can make it their job in their life to do so. If the technology can be invented, then on the other hand, it can also be hacked. So there's definitely an upside and a downside to it. Just like in all hackers, currently, like hackers that are caught are generally picked up by the government to actually catch the next hackers. And so basically half of our security is being built by the people that can break them down. So you can't really prevent people from becoming good at breaking down the security if they're also the ones that are good enough to build it. So that's what I think.
Okay, thank you, Alec. So now I'd like to stick with this theme of going back to last week and invite John Menard up to talk about the experiment we did, which involved using thermocouples and calculating the time constant of the thermocouple. So if you don't mind giving me just 1 second to get that up.
I don't have a table topic.
You just have that.
Edit that out. Alright, so last week we did an experiment involving thermocouples and time constants. We did 2 experiments. We did a boiling water experiment and an ice water experiment. I have a diagram of how a thermocouple works. It works with 2 wires wrapped around sort of a little cylindrical place. They emit a current through wires into a transmitter. This current varies with temperature, and through this, these varying currents can be read. The goal of the experiment was to analyze data recorded in order to find the time constant for thermocouples. We did this using Excel and a computer. Below are some of the equations we used. We used one called normalized temperature, which is how we got the slope of a line to find a time constant. T infinity was the temperature of the medium, which either was boiling water or the ice water, and then T initial was the initial temperature used. All right, here we have a plot of our first experiment, boiling water experiment. As you can see, at time 0, we dropped our thermocouple into the boiling water. As you can see, the temperature rose quickly, and once we took it out, it took a lot longer for the temperature to normalize. Our initial temperature was 23 degrees Celsius, and the temperature of the water was 100 So here we use the normalized temperature to find the time constant. How we did it is we would put the temperatures into our formulas here. We would find the slope of this line, and we would then take the inverse and multiply it by -1 to find our time constants. For the boiling water, when we dropped it in, our time constant was about 0.42, and when we took it out and let it normalize in ambient air, our time constant was about 90. Next, we did an ice water experiment. Our initial temperature was about 23, and our other one was about 1 degree. As you can see, pretty much the same result, except the graph is just flipped over. Again, we plugged our initial temperatures and our final temperatures into our formulas, did a plot, we found the slopes, and we inverted them and multiplied it by -1. For the cooling phase of the ice water, we got about 0.147. For the normalizing phase, where we just let it sit in ambient air, we got about 83.
So, John, since with all this data we have now, how can we use this data to impact future experiments?
Well, we could check the calibration of our equipment. One thing we checked online is that you can check a time constant by looking at about once a temperature change hits about 63% of the total temperature change, where a time constant usually is around. So I was able to go and look at our graphs and kind of verify, our time constants made sense.
I have a question. Okay, yeah, you can follow that. It's 3 minutes, but
Okay, so thank you very much, John. And now that that experiment's been talked about, I'd like to invite Davis Lambert up to talk about the experiment we'll do next week. From what I understand, we'll be doing a steam calorimeter. And so Davis will be here to shed some insight on what that is. And let me pull that PowerPoint up.
Okay, as Eric said earlier, my name is Davis Lambert, and I'll be going over the process for the steam calorimeter, experiment number 2. So first off, we're going to be determining the quality of the steam, which is basically the amount of vapor or rather dry steam, and a 2-phase mixture, which would be a liquid and a vapor. These calorimeters are going to be in series, as using just one individual calorimeter won't successfully remove enough of the liquid so that it can properly function, and as I explained already, what quality is. So the relationship with thermodynamics, we're going to be looking at mostly the first and second law, as you'll be seeing in a little while with some of the equations we're using. And we're going to be looking at different states of vapors. We're going to have our superheated, our two-phase mixtures, as well as our saturated vapors. And we're also going to be looking at temperature versus volume and temperature versus entropy diagrams. So the objective of this is to determine the quality of the steam throughout the cycle. And some of the practical applications of this would be controlling the quality. If you're using a steam power plant, you obviously want to control how much quality is in the vapor, depending on what mechanisms you're using. Some of them won't work properly if you're using too much quality in that specific mechanism. And then with that, ensuring the longevity of these devices by maintaining that quality. So here's the apparatus. Right here we have the separating calorimeter and the throttling calorimeter, as well as the condenser. So there's just a picture, and then we'll be reviewing the handout schematic in a little while for reference. So some of the tools, as I said, the main three, the separating calorimeter, the throttling calorimeter, and the condenser. There'll also be valves throughout, as well as some beakers, but those are the main three that we'll be focusing on. So the procedure, we're going to be opening up the PDAC program. We'll be connecting the pressure transducer and thermocouples to appropriate channels. Afterwards, we'll verify calibrations for different differential pressure transducers. And we'll start the flow of cooling water through the condenser by opening the red valve below it. After that, we'll be draining the separating calorimeter several times to make sure that there's no condensate in there. Of course, it has to be above a certain height because if there's too little, it won't work. Then we're going to start taking data by switching the throttling condensate valve when the initial fluid level in the separated calorimeter site class is around 200 milliliters. And at the same time, we'll be logging data on the PC. And we'll continue collecting condensate until the fluid level in the separating class has risen above 400 milliliters. After that, and after it's reached about 400 milliliters, we'll quickly close valves 11 and 12, which on the schematic are both labeled as throttling condensate valves. That's why, just for reference to see which ones those are, to avoid that confusion. We'll be closing 11 and opening 12, and we will measure the volume or the mass of the condensate in the throttling condensate collection beaker. We're going to repeat this about 4 times. After that, we're going to allow the apparatus to cool down, and we'll turn off the condenser cooling water. And after that, we'll just clean the entire area and make sure we left it as we found it. So some of the relevant data will be the saturated steam tables, the superheated steam tables, and a TV diagram. Some relevant equations, these were supplied to us through the lab manual, just two of them looking for the entropy of stage 3, which is between the separating calorimeter and the throttling calorimeter, as well as the entropy after the throttling calorimeter, which is when it will be a superheated vapor, as well as the collected, a kind of summated equation looking for the quality of the area between the separating and the throttling calorimeter, and then lastly finding mass balance, using mass balance to find the quality before the separating calorimeter. Some of the predicted results, using some of the steam tables, it was asking for the pressure going into the separating calorimeter, and it got around 0.6178 megapascals, and as well as at the second half, assuming we had a quality of 0.95, what the temperature and the pressure would be after the whole thing, the throttling calorimeter. And it was a large range. You kind of, typically the entropy stayed the same for each. So I kind of estimated around 340 degrees Celsius and 0.5 MPa. So the conclusion is that you can control the quality depending on the temperature and the pressure going in, as well as how the calorimeters are calibrated. And you can use this to apply to steam power plants and elsewhere.
Okay, well, thank you, Davis, and thank you once again to John and Alec, and I guess that's it for this week.